All right, so hello everyone. In this video, I'm just going to show you how to find a confidence interval for a proportion. This is an example that we didn't have the time to cover in class. It was written in the notes, so I'm just going to go over how to solve this. So we have that we're trying to estimate the true proportion of a given population, which we denote by the letter P, and from a sample of size 1060, we find a proportion of 0.57. This is the estimator. We're going to find a 98.5% confidence interval for the population proportion, right? So again, just a reminder on confidence intervals, we have a population, and in this population, the true proportion, which we don't know, this is the thing that we're trying to guess, is what we're trying to estimate. So this is the population. And all that we get from here is a given sample that we can study. So this is the sample from which we get that the sample proportion is 0.57. And what we're trying to say is, based on the sample that I chose, what is the best guess that I can make for the parameter of the population? So I have that the confidence interval for a proportion is given by p hat plus or minus z alpha over 2 times square root of p hat times 1 minus p hat divided by n. But there's a warning here. Remember I said there's usually strings attached, and in this case, those strings attached tell us that we need to make sure that first, n times p hat needs to be larger than 5, and n times 1 minus p hat needs to be larger than 5 as well. So we're just going to check that by plugging in n and p hat into our expressions over here. So over here, we're going to have 0.57 times 1060, which is equal to 604.2. And this is larger than 5, so we can check that part. And over here, this is going to be 0.43 times 1060, which is going to be equal to 455.8, and this is also larger than 5. Okay, so we don't worry too much about why this needs to be true, and this just comes from the math that somebody else did for us, but we do need to make sure that these things are satisfied. All right, so now that these things are true, they're checked, everything's okay, I can actually try to plug in everything into my expression over here. And I already have the values of p hat, which I will be able to plug in here, here, and there. I have the sample size, which is n over here. That means I'm going to be able to plug this in here. And of course, the difficult one is always going to be to find the z alpha over 2 over here. So for that, we need to go back to our z distribution. That's why we have a letter z over here. And find the value that corresponds to having 98.5%. So if we look at our distribution, that means that we're going to have to get 98.5% in the middle over here, which means that if I chop from each of the sides, I'm going to have 1.5% chopped from each the top and the bottom. So that means 1.5% is 0.75% chopped from the top and 0.75 chopped from the bottom. And if that's the case, then that means I'm going to have to look for the value over here that corresponds to this in my Z table. So I'm going to go back to my table and look for the value that corresponds to over here, this number over here. This is going to be 98.5 plus 0.75, which is equal to 99.25. And the value that I'm trying to look for is the boundary that corresponds to this over here, which based on this notation is Z 0.0075. Oops, box is a little bit too small there. Just that. So Z 0.0075, which is this over here, right? So it's half of what I'm chopping from both sides. So this is 0.75%, which is the same as 0.0075. All right, so that means inside the table, remember the filling of the table for the Z distribution, the filling of the table corresponds to the filling of the area, right? So this is the filling of my table. And what I'm trying to find is the corresponding margin. So this corresponding value. I had already tried it. Okay. So what you're going to do is you're going to go to your table and you're going to look for when the filling is equal to 0.9925. So in your table, you're going to have 0.9925. And so if you look for this in your table, you'll see the right value will be 0.9927. And this value over here will be 0.9922. You can even go so far as to say this is going to be 0.9901, just so that you find it, 9901 and 0.9943. Right? And then you'll have like other values here and here and here and here. So when I'm saying look for this in the filling, it means inside the table. And so this corresponds to the value of the area. Right? So this is the value that we were looking for. And now the value of Z is going to be what corresponds to this margin along with this one over here. And if you look in your table, this is going to be equal to 2.4. And here this says 0.03, right? Which means that our Z alpha over 2 over here is equal to, so Z alpha over 2 is equal to 2.43. And now I can plug this into my expression as well, right? So what I found here is the value for Z alpha over 2, which I will now replace into the formula that I have for the confidence interval. So my confidence interval now that I know how to plug everything in is going to be equal to, the confidence interval will be 0.57 plus or minus 2.43 times square root of 0.57 times 1 minus 0.57, which is equal to 0.43, divided by 1060. If you plug this into your calculator, and here I usually try to evaluate the whole term over here at the same time, because if I try to do it like piece by piece, I'm going to end up having several rounding errors that might compound and make my result a little bit too far from what I actually want. So if I just plug everything at the same time there, I'm going to get that this is the same as 0.57 plus or minus 0.03695. Which, if I write it in terms of percentages, and I round a little bit more, so here I just kept a lot of them so that you can check if your result is correct. But this is the same as saying 57% plus or minus 3.7%. Right? And so my confidence interval here is 57 plus or minus 3.7%, which is the same as 53.3% to 60.7%. And now I emphasize a lot on how to interpret these because I think that's the most important part of this section. And what I wanted you to remember about this is, okay, so we have that the confidence interval, so we are the confidence interval with level of confidence 98.5% for the true proportion is 53.3% to 60.7%. Right, and so that's just me saying what I know, which is I applied a formula and I found this interval. But that's not really the interesting part over here. The interesting part is to say what that means, which is that I am now 98.5% confident that the true proportion is in this interval, which means I don't know if my true proportion is in this interval, but I know that if I took many samples of size 1060, 98.5% of the samples shows, of the intervals computed in this way would contain the true parameter. Now, that doesn't mean that our particular confidence interval contains a true parameter. It just means that I am 98.5% confident that it will contain the true parameter. This means that I am 98.5% confident that this interval captured or contained the true parameter. But of course, the big lesson over here is that we never know if it actually does contain the true parameter. Now, I want to end this with a little note on the fact that this is an example that we had talked about at the beginning of the week, which was the case where we had a sample of students that answered that they made friends online. So we said 57% of teenagers said that they met friends online from a sample 1060, and then the article had cited a margin of error of 3.7%, and this is where we get that 3.7%. So essentially what the article did was to construct a 98.5% confidence interval for the proportion. Of course, the article doesn't have any extra information that we don't, so that means that they also don't know if the true parameter is within these bounds, but based on the information that they have, this is the best guess that they can get. That's it.